It's really 30 minutes. It's just 70.
So I guess we'll slowly start, we'll warm ourselves out into the lecture. So let me remind you that we finished the last lecture by discussing the concept of single particle state, which will be our building blocks in producing many particle wave functions. So then, if I have a set of single particle states and I use the notation little psi p as a function of a single fermion electron as appropriate, then certainly if I have a many particle wave function, capital psi, which is a function of n sets of these single particle coordinates, then it is pretty much obvious that I can write the following expansion. I have some coefficients, I'm going to call them d, labeled by indices p1 through pn. And, they run like all the p's, from 1 to the size of your basis, say infinity, if you're using an infinite basis set. And then we have products, psi p1 x1 through psi pn xn. Okay? Clearly, this is something I can always do, and these coefficients d here, from the fact that our single particle states are orthonormal by our assumption, can be computed by forming an inner product of our single particle states with indices that correspond to what you see here with our wave function. Of course, if you want to do it explicitly, we're not going to do this many times, but as a reminder, since those are the early lectures, now of course you will have to form a product of n single particle states and then integrate this with the wave function, which means perform a very complicated integration. That's what we're talking about. And fermions, so you have to integrate over all coordinates of all these fermions. That is not easy, obviously, in general, because typically our wave functions are very complicated. Anyway, but formally we can always write this. Now, this, of course, is not telling us anything about what our wave function psi is. I can write this expression for a wave function of bosons or some other particles, okay? Because I'm not imposing yet a condition that our wave functions for many-Fermion systems, for systems of identical fermions, should be anti-symmetric. So let's see what is the consequence of the anti-symmetry of our wave function that we discussed also last time on this expansion. And in order to do this, I will introduce an operator, which I will write with this script A, which is an idempotent anti-symmetrizer. I will move this up in a second. Okay? Let's do this. All right? How do I define it? I'm going to define it as follows. It's 1 over n factorial. And then we're summing over all permutations of n indices. So I think I talked about the group of all permutations of n symbols. I'm going to call it Sn. If I haven't, well, then I'm defining it once again. And then we have signs of permutations multiplying the permutations. Okay? That's a formal definition of this anti-symmetrizer. I call it idempotent anti-symmetrizer because you'll be able to prove, and that's actually one of the questions in your homework, you can prove that if you do a squared, you end up with an a. You can also prove, that is actually trivial, so I'm not asking you to prove it because it's really obvious, it is also Hermitian. Well, you know very well that if an operator is Hermitian and idempotent, it's a projection operator. In mathematics you can actually prove it, that any operator that satisfies these two conditions must be a projection operator corresponding to some subspace. Well, in our case, this is a projection operator on anti-symmetric states. That's what it does. And if you really want to connect the dots together, if you go back to your group theory reading or classes, and I put actually some books on reserve about, like Morton Hammermesh. I love that book, for example. That's why I put it there, obviously, because I like it. Well, then, you remember how projection operators are defined in group theory. What you have here is the dimension of the irreducible representation. In our case, it's 1 because we have anti-symmetric states, then here it's a number of elements in the group. That's n factorial for permutations. You're summing over operations in the group. Those are permutations themselves. Then you have, symmetry operations, permutations, times the characters. Well, here there are plus or minus because we have only even or odd permutations. So it's going to be plus or minus 1. So you see, this is a very logical definition. Nothing really unusual. But it's a useful one because of these properties. So I'm going to now try to utilize these definitions in some sort of a calculation. Yes?
A notational question. The region over which you're summing, Q is contained in a set of, I don't understand what the third
The
symbol
Sn?
is.
Sn, yeah, it's some sort of, okay. It's some sort of script S. My attempt to produce that script. Okay? All right. Okay, so, thank you. Going back. So, so we know that our wave functions are anti-symmetric. So if I take a wave function psi, and if I project it on the on the space of anti-symmetric functions, then I should not change it, because for fermions, it is already anti-symmetric. So I'm going to use this equation in conjunction with the first expansion, the one on the top, to see what we can obtain. So the wave function psi is the result of applying A to psi. I'm going to apply that A to the linear expansion on top, okay? It's a linear operator, so I end up with a sum over P1 through Pn. Okay, there are dots here. Then we have d, little d, P1 through Pn. And then we have this anti-symmetrizer acting directly on the product of n spin orbitals, right? I'm going to now use the Dirac notation. So what we'll have here, I'll write this in this way. So we have psi P1 through psi Pn. This is really the product that I wrote there in a coordinate representation. So if you want to be really formally elegant about that, what you have here is the tensor product of n single particle states or spin orbitals. Okay, so let's agree on the notation that if I write something like this, what I mean it's a product, just a simple product of these states. Okay. All right. Well, let me now perform a little straightforward manipulation as follows. I will stick 1 over square root of the n factorial here. Okay, multiplying the d's, and then I will of course have to have it back so that it cancels out, and then anti-symmetrizer acting on our psi p1, psi pn single particle states. And now I will introduce new definitions. That is, I will call these rescaled coefficients capital D. And I will, so this is going to be called, in a moment, when I spell it out, capital D. I will call these rescaled anti-symmetrized products, rescaled of the square root of n factorial. I will call them capital Ph's. Okay, some sort of functions that we need to understand. Okay, before we understand them, let me also put a little bit more notation here. Sometimes I will write these states that you see here defined in a circle as phi, P1, Pn, that is states that are simply labeled by a bunch of indices. Sometimes I'll write them in this way, P1 through Pn, okay, which means that you can see what I'm doing. Compared to the original situation, I am having a bunch of single particle states in the cat, right? That's a simple product. When I put these curly braces, what I mean, I anti-symmetrize them. Okay? So this is no longer a simple product. It's an anti-symmetrized product. And I'm going to try to be consistent with this notation. But as you will see throughout the course, sometimes I like to use this one. Sometimes I'll prefer that one. It depends, what I'm writing. So please be ready for sort of both. Okay? And don't get surprised when I do that. But of course, we can always go back and redefine these things as the need arises. In any case, what we have now demonstrated is this. We showed that our wave function psi belonging to the anti-symmetric wave functions has the following representation. You're summing over indices P1 through Pn. Let's make those dots nice. Capital D coefficients that I introduce over there, and I will write them one more time. They are defined as 1 over square root of the n factorial lowercase d p1 through pn. And then these new functions phi, labeled with indices p1 through pn, which we have defined to be, as you can still see on the left blackboard, square root of the n factorial times the anti-symmetrizer acting on the product of n single particle states. Okay, that's what we have. So let's now try to sort of understand these objects that we see in our representation. Let's start with the functions phi. What are they? Well, you know, if I don't know what to do, I'm going to go back to the definitions. And I still have a definition of my anti-symmetrizer over there, so I'm going to apply the definition to the phi. Let's see what comes out. So we have phi, p1 through pn, equal to, we have square root of the n factorial, but please note that there is 1 over n factorial here. So that will cancel out. You will end up with 1 over square root of the n factorial. And then we'll have, according to our definition, a sum over permutations, where Sn is the group of all permutations of n indices. Then we'll have the sign of each permutation in the summation. And then we have to apply this permutation to our coordinates. Okay, so if I write it in a coordinate form, this will be psi p1, x q1. In other words, index 1 became q1. I just permuted it. Then you have psi p2. Let's just write a little bit more than we normally write. So that's going to be the second one. 2 got permuted into q2. And then in the end, the last one after some dots, we have psi pn x qn. That's what you end up with. And that is, of course, the coordinate representation. So in principle, if you want to be really strict, you should write here x1, xn, meaning the value of this function at a specific choice of your coordinates. So you can see that's what I get. Well, you know, I can also write this. Maybe that move this up a little bit. We can also write this as 1 over square root of the n factorial, sum over permutations. And then we have sine. And instead of permuting coordinates, as I'm doing here, I will permute indices. That's equivalent. So it's going to be psi p. Now, you know, lots of indices, so please bear with me. You know, 1 here will be replaced by q1, but I'm not going to touch the coordinates of our fermions. Then psi p q2, x2, and dot, dot, dot. In the end, we have psi p qn xn. Well, let's now try to read this expression. If you now go back to your algebra.
It would be the inverse.
Well, but yes, it will be the inverse, but the sign of the inverse is the same as the sign of the one you are trying to invert. So we can do this. Excellent remark about this. Okay, so now let's try to understand. If you go back to your algebra classes, you know, probably nowadays, based on what I know about my daughter's education, that's high school math now. That's a definition of the determinant. Okay, what kind of determinant? Okay, so let's try to write it. Phi, p1 through pn, is a determinant which will have a factor of 1 over square root of n factorial, and then the matrix that needs to be written for this determinant consists of our single particle states, or spin orbitals. So I'm going to write it like this. Psi p1 x1, psi p1 xn, and then we'll have, say, let's write the second row, psi p2 x1, psi p2 xn, and of course, you know, let's put some dots here, and let's write the last row, psi pn x1, psi pn xn. So it's an n by n matrix, and you're forming a determinant of it, and that is simply right there in the definition. So if I say want to do it for, say, let's imagine I have 2 electrons in a molecule, or 2 fermions, or something like this, some other 2 fermions, then what would be a determinant, say, phi p1, p2? Well, you know, according to our definition, this will be 1 over square root of 2 factorial, I should say, but that's 2. And then what you have is going to be simply psi p1 x1 psi p2 x2 minus psi p1 x2 psi p2 x1, right? So that's what it is, and you can do it for the 3, for the 4, and so on and so forth, and see how they look like. The main point now about these determinants is that, first of all, we call them Slater determinants. In recognition of John Slater, one of the most famous quantum mechanicians or scientists in history. Okay, you know, he introduced determinants, he derived the Anticommutation equations, and so on and so forth. Lots of course, he made huge contributions to DFT in the form of the X-alpha theory in the 50s, and so on and so forth. So, an incredibly important name. So we have Slater determinants. Okay. Now these Slater determinants, and I'll try to prove this a little bit in a few minutes, not right now, are normalized to unity. They are mutual orthogonal. And of course, what is important right now is that they are also anti-symmetric. Okay? Clearly, you know, that is a property of the determinant. If I flip, say, 2 columns, so that means switching x1 with x2, well, that will change the sign. Okay? But there is more. And that more is important right now for what I want to prove. Okay? So, actually, here. What's more about it is the fact that I can also permute the rows. Okay? That also does produce sign changes. If I say flip P1 and P2, that will change the sign. So the determinants that we have here have properties such as, for example, this one. If I say do feed P2 P1 and then P3 up to Pn, well, that will produce minus feed P1 P2 P3 through Pn. Okay, so in other words, if you permute your indices, you're just changing the sign according to the permutation you're applying to it. Okay, we'll take advantage of this.
That's what you mean by anti-symmetric.
Sorry?
That's what you mean by
Yes.
anti-symmetric.
Well, they're anti-symmetric sort of in 2 different ways. They are anti-symmetric with respect to coordinates that we have, and they're also anti-symmetric with respect to indices that define our spin orbitals in the determinant. And, okay. Well, okay, so we know around a little bit about our state determinants. Let's talk about our coefficients D over there. What kind of properties do they have? Well, you know, let's start with some calculation again. Not to second guess these things. What is little d? I still have, no, I guess it's already buried, but it is still there. I can erase it. Isn't there? I have them somewhere. I guess I have to erase. Okay. Well, let me remind you what they are. We compute them as product of psi p1 through psi pn with a psi. That's the starting point for our considerations. I'm going to do the following now. We know that our wave function psi is anti-symmetric. So I'm going to stick the anti-symmetrizer here because I know it doesn't change anything. Okay? So what you end up with is psi p1, psi pn, inner product with a psi. But A is Hermitian. We already talked about it. So I can use turnover rule and move this A in this location. Okay, well, that will produce an anti-symmetrized product state, psi p1, psi pn, psi. Then, if you look at our definitions of phi over there, see what I can do is I can now throw square root of the n factorial here, and I can then divide by square root of the n factorial here, okay? And then I have square root of the n factorial anti-symmetrizer on the products of the states. That's our Slater determinant. The definition is still over there. So I will continue then and end up with 1 over square root of the n factorial. And here now I will have a Slater determinant phi, p1 through pn, inner product with a psi. Okay? And now if I want to see what our capital D coefficients are, those are the ones we'll eventually need. Well, you can see that we now are proving that the capital D coefficients you know, you can see that you have to divide by 1 over square root of n factorial one more time. So it's going to be 1 over n factorial altogether. And then we have an inner product of phi p1 through pn psi. Sometimes you'll hear me saying an overlap of two functions. In chemistry, quite often we say that. So, you know, I will, I guess, use, you know, depending on the mood, scalar product, inner product, or overlap. So, what you see here is an overlap of our wave function with a Slater determinant. Okay? That will be a language of chemists who talk about overlaps very often. Okay, let's move this up and let's try to read or interpret what we have written. First of all, what we see is that our coefficients D have the same anti-symmetric property with respect to indices as p's themselves. Because, you know, if I flip p's here, I'll flip them also here. Okay? So if I change the sign here, it will propagate into the change in the D. So in other words, I can also say that D P2, P1, P3, so if I permute P1 and P2, is a negative of D P1, P2, P3 through Pn. So let's remember these little properties that are kind of handy when you analyze it. Well, first of all, one of the consequences of all of this is something extremely important for us, namely, so what if, say, P1 and P2 are equal? Okay, well, if P2 and P1 are equal, you have PP here, PP there, but there's a negative. It means that that coefficient will be 0. Well, if you go back to our Slater determinant, exactly the same will happen. Is this a surprise to anybody? I guess not. Because that means that we are trying to make two rows identical. You know that in mathematics, if the determinant has two identical rows, that's a 0 determinant. Are we surprised it's a 0? No. Because we have fermions, you can't occupy the same spin orbital twice. That is the Pauli exclusion principle, right in front of our eyes, in the form of Slater determinants. That's one of the reasons Slater introduced them, to make sure that our electrons are treated properly with respect to the fermionic algebras. Okay? So let's remember about it. And now I'll use all these different features to go back to our expansion of the wave function. It's still there on top. You can see a summation over all these p's and the d's. But let's leave space here for a second because I'll start doing some manipulations. First of all, since these coefficients are 0 when two indices in them are equal, that means that I don't have to sum over all the p's independently. I can assume that my p indices in the summation are different. Because if I make them equal, the coefficients of the determinants become 0. Well, then if that's the case, I can do one more thing. I'm going to do it below. I can simply write this as a summation over ordered sets of indices. Okay? And let's see what else do I have to do if I try to do this. You know, if you have a set of different indices, then they are a permutation of some ordered set. Okay? Some permutation. So, and obviously since I'm summing all of them, then I'm going to end up with a summation over ordered sets and then all possible permutations. Okay? What do these permutations do? If you permute indices here and you do it simultaneously here, you don't change the sign. Because it's either plus, or minus. Okay? So it's plus in the end all the time. So what I can do to remove these redundancies, I can write this as n factorial dp's here, summing over ordered set, okay, times the phi. Well, that is becoming interesting. I'm going to call these coefficients c, little c. Because eventually I want to end up with something which we call a CI expansion. Okay? Let me try to build this over here. What we have just demonstrated is that psi can be represented as a linear combination with coefficients little c using Slater determinants where we're summing over linear independent ordered set of indices, okay, and the little c here is n factorial times our original d coefficient, but as you still have it here, you see this is an overlap of phi and psi, and you have 1 over n factorial, which will cancel that n factorial, so you'll end up with a very simple formula for the c coefficient. Simply form an inner product of phi with a psi. Well, certainly this rings the bell now, because we are saying that Slater determinants provide us with a basis for our many particle wave functions in the fermionic systems. Okay, you can see that any wave function, I didn't say where it comes from, any anti-symmetric wave function or a function of n particles is a linear combination of all possible Slater determinants that you can come up with from your single particle basis. Okay? And if you want to know these coefficients, of course we rarely know them exactly, but if you want to know them, if I know the wave function, that's how I calculate them. Well, that's exactly what you do when you try to represent functions in terms of orthonormal basis. That's how you compute them. Okay? So this is fundamentally extremely important. But of course, to convince ourselves that everything is right here, let's just finish on the point that I mentioned when I did the proof, that is that Slater determinants are orthonormal. Okay? So let me do it on the next blackboard. I'm going to keep that up. And you will see that actually this anti-symmetrizer is a useful thing to have around for these kinds of considerations. So what I want to demonstrate is this. I want to form an inner product of two Slater determinants. We already know that they form a complete set because I can represent any Many-Fermion function as a linear combination of them. So they form a complete set. Let's convince ourselves that they also form an orthonormal set for many-particle states. So I will try to form an overlap of two Slater determinants. One has indices P1 through Pn, another one Q1 through Qn. Okay? Just like that. So, what you do next, you just use your definitions. Okay? So, you remember what phi was. Phi was the square of the n factorial, you can kind of still see it there, times the anti-symmetrizer times the product, right? So I'm going to get square of the n factorial from the leftmost phi, square of the n factorial from the rightmost phi, and then you end up with an anti-symmetrizer acting on the product of psi p1 through psi pn. That's your bra. And in the ket we have an anti-symmetrizer acting on psi q1 product of psi q1 up to psi qn. Now I'm going to manipulate this expression a little bit. So obviously the first one is trivial. That's n factorial. So that's it. And then I'm going to use turnover rule. That is, I'm going to move a over here. We know a is Hermitian, so I can do it almost immediately, right? So we have then psi p1 through psi pn, and then what you end up with here is a squared. Okay? If I do that, a will go here, will produce a squared. What is a squared? I said in the beginning that a squared is a, because it's an idempotent operator. So I don't need two, I just need one of them. So it's going to be a acting on the product of psi q1 through psi qn. Well, I guess at this point we have to spell it out to make further progress in our calculations. So we end up with n factorial. Now I'm going to use the definition of the anti-symmetrizer. You remember it had 1 over n factorial in front, right? Then we'll have a summation over all the permutations in our group of permutations of n indices, a sign of a permutation, and then we'll have simply, I write it explicitly, here we have a product of n spin orbitals, so it's going to be psi p1 star x1 up to psi pn star xn. That's what you have on the left. On the right, we have permutation from the A in that summation acting on this product. I'm going to be permuting indices q1 through qn. So I end up with psi say q, q1, that's fine, x1, and then psi q, qn, xn. Okay, after permuting it, of course, we integrate over all these coordinates of all the fermions. So in the case of electrons, there will be 4n symbols of an integral. I'm not going to do that. We all know that that's what it is. I'm going to do it explicitly. I want to analyze this expression now. Okay, what can I read from it? Well, the obvious thing I can read from it is that this cancels out. Well, that's nice. All right, something goes away. But let's read the rest of it. So there are two possibilities. We know that in our expansion we need to consider only the ordered sets of indices because the other ones can be obtained by permuting and changing signs. So there's no point really in looking at them. So I'm going to assume that in our determinants P1 is less than Pn, and then Q1 is less than Qn. So we have these two ordered sets. Okay. Now let's think carefully. If any of these Q's here, little q's I mean, is different than all the P's, okay, meaning that these two determinants are different, then you get a 0. That's from the orthogonality of our single particle states. So I say it again. If any of these little q symbols, okay, are different than all the P's, then at least one of the spin orbitals here will be different than all of them. And that one will run into its partner, you integrate over, and you get a 0 from orthogonality. So we know already that when these two sets are different, okay, so if P1 is different than Q1, P2 different than Q2, and so on, then we get a 0. That's orthogonality proved right away. Okay, so let's look at the interesting case where these two sets are identical. Okay, so what if, let me write it like this maybe, what if P1 equals Q1, P2 equals Q2, and Pn equals Qn? Well, if that's the case, then let me rewrite this actually, so that we don't have to second guess all of these things. Maybe I'll do it here. Okay, so what we can see is the following. Then you have an inner product of phi P1 with itself. Okay? And then if I read it from there, then factorials are gone. So we have a summation over all permutations. We have sign of a permutation. I'm just copying from the other blackboard. We have an integral, and I have psi P1 star x1 through psi Pn star xn. But I am saying that all the little q's are now the same as little p's. So this is P1, this is Pn. Okay, so let's continue writing. I guess I cannot squeeze it here, so I write it right here. It's going to be psi q P1. It's P now, Q permuting the P, up to psi q Pn xn, and of course then we integrate over all coordinates. Well, let's now look at this one more time. So if this permutation is not identity, say suppose you flip P1 with P2. Well then P2 will be here, P1 will be there. That P2 will run into P1. But P2 and P1 are different. So because of orthogonality you end up with a 0. Okay? So you can see that any permutation in that summation other than identity produces 0. Well, that means I don't have to sum over all permutations in this case. All I need to do is to simply say, choose one term, identity. Well, then everything gets very simple. Sign of identity is 1. Okay, and then I have an integral of psi P1 star, let's write it one more time, psi Pn star xn. And then here, if Q is identity, you're not touching your symbols. So QP1 will be P1, QP2 will be P2, and so on. So you end up with psi P1 x1 through psi Pn xn, and again integrate over. Well, obviously, this is 1, because it's a product of integrals. Integrate psi P1 with psi P1, psi P2 with psi P2, and so on. Each of these integrals is 1, so you're multiplying a bunch of 1s. That is 1. So we just proved that these states are not only orthogonal, they are also normalized to unity. Okay? So that means they are orthonormal, they are complete, they form an appropriate basis set for many particle states. And this is actually a basis of the whole theory. It's not like we have to second guess how the wave functions look like. We already have one theorem. You can always write an exact wave function as a linear combination of all possible Slater determinants in a basis set. If you limit your basis set in practical calculations, then of course there's going to be a finite, very long expansion. I'll come back to this, called full CI. But it still will be exact in that space that is limited by the number of spin orbitals. So this is fundamentally very important. So now we would like to switch gears. I'm thinking, I promised you this little break. So I think it's a good point at this time. Now we're going to be switching to second quantization. So let's have a little break. Then we'll restart in a few minutes to move from this representation, which we still see on the blackboard, okay, into the new form of these considerations, which we call second quantization. Okay? So let's have a little break for a few minutes. And of course, this may be, if you want to ask me questions about what we just discussed, that's a good opportunity.
So in the case of 2D, is there only one possible Slater determinant? Because you have the permutations ordered?
In terms of, you said
Like P1, P2, 2D. So there's
No, because then the P's are summed over, there are many. So you can have, say, 2 electrons, right, or 2 protons, right?
Yeah.
And then you have, but it's still your P's go from 1 to the number of single particle states. So there are many 2 by 2 determinants.
Oh, yeah.
Yeah, so it is, then, of course, you can choose a representation where you just choose to use one determinant. That's the basis of Fock theory. We'll talk about it at some point, but that's already an approximation.
Okay.
That's no longer exact by any means. Okay, that could be a good approximation. We can always debate that, and I will talk about this too, but certainly it's no longer exact. But of course, you can see that if you use this language, it doesn't look very appealing. I mean, you have to do that hard work, but all these factorials, all these things written up this way, of course, that can be very laborious. Because imagine if n, that number of electrons or particles, is not 2, but say 100. Not a big number even, right? You're not even close to halfway through in your nuclear tables, right? In chemistry, of course, 100 electrons, well, not a big molecule anymore. All right? So you can see that this is not the language. The reason we're going to be switching to a different language is exactly because this sort of language is appropriate. It's of course correct and so on and so forth, but it's not very convenient when you want to develop sort of generic theories or approximations applicable to all many-electron systems, not just to some of them. Okay. All right. So let's see. Okay. It's nice outside. Nicole, how are you doing?
Doing well. A little cold.
Is it what?
It's cold.
Oh, it's cold out there. Okay,
Yeah.
it's interesting. You know what? I may actually want it to cool myself a little bit, because it's quite warm at the break. So that it's colder, right? So you get a little flow from here.
Yeah.
Ah. Okay.
Oh, if you could ask them to give comments on the video, that would be great.
Yes. So if you want to say something, we're being recorded, but if you want to say something, you want to continue a little bit in the break. Of course, it's okay if there's silence. Comment on. In the meantime, I'll start arranging things so that we have space for you. Yeah, it's like this. Always good to lecture in the morning because this is where the blackboard is extremely pink. The QRs is no longer so good. So we have a big advantage.
So this already tells you you're going to have partial occupation.
Yes, we'll talk about this too. Yeah, so the partial, okay. In the language of determinants, there is nothing like partial occupation. Every determinant has a state occupied in it. We'll talk about it in a moment, or unoccupied.
Yeah.
You cannot have it in between. But if you form a linear combination,
Yeah, then,
and then you compute a reduced density matrix, because without it, there's no concept, there's no mathematical concept of, every determinant has its own specific occupation numbers. But of course, if you want to now compute, you take this linear expansion of determinant in terms of determinants, and then if you compute the reduced density matrix, and then you diagonalize it, I'm talking about a one-body reduced density matrix, so you integrate psi star with psi over all particles but one, you multiply by n, that's an n-fermion or n-electron in case of chemistry density matrix, and then if you diagonalize it, then you end up with the concept of natural orbitals. Okay, so, and then you will have fractional, then you will have orbitals or spin orbitals with some occupation numbers, right? So in typical case in chemistry, the core ones or the low-lying ones will have an occupation number close to 2, because we're talking about spatial orbitals that can be occupied with 2 electrons, spin up and spin down. Okay, and then as you approach the valence shells, you suddenly start seeing numbers like 1.95, 1.9, 1.8, and it now depends, right? If it's a closed shell molecule, they will never be very far from 2, and then you will have lots of, at first, very small numbers around 0, like 0.1, 0.05, and so on, and then eventually 0. If the molecule is a biradical, you will have in the valence shell sort of the highest occupied orbital will have a number close to 1, and the lowest unoccupied orbital will be close to 1 as well. That's going to be actually, we call this biradicals in chemistry. I think you call it in nuclear physics borromean nuclei. I think helium-6 is a good example. Closed shell plus 2 particles outside the closed shell. Right? Yes, so these fractional occupation numbers are actually they're very useful because they give you the interpretive tool. Looking at the full CI expansion isn't easy, but thinking in terms of occupation numbers, of course, is extremely good. If you just want to get a sense where my particles go, do they penetrate these orbitals or those orbitals, right? But computationally, we still have to deal with these expansions, right? I mean, that's what we really have to spend our time on. Excellent. Okay. This as well. We can leave this one for now. It's a useful one. Ready for a restart? Okay, all right, so let's continue. So as I said, so we now proved this fundamental theorem that allows us to expand many-Fermion wave functions in terms of Slater determinants. And we know, of course, their properties. One of them was that when you permute indices here, okay, you change the sign. And the question now is this the convenient language? And is this really a necessary language? If we wanted to follow this language in first quantization and in a normal coordinate representation, it would be very complicated. Because, as I said, you would have to sort of treat every problem as a separate problem. If I want to do a helium, 2 electrons, find a basis set for it, and produce an expansion. Okay, then if I want to do lithium, that's 3 electrons, I would have to redo this again. Because, we have this explicit dependence of this expansion on the number of particles. I want to get away with it. So I have a theory which sort of doesn't use the particle number as my most important number. It is eventually the number you're going to have to know, but not in your formal considerations. That's the language of second quantization. Here we have to simply realize the following thing. What is that you have to know to write the determinant? All you need to know about it is what single particle states are occupied in it. That's all you need to know. Once I give you these indices, 1, 2, 3, 7, I mean, you know already which determinant it is, right? Our fermions here are indistinguishable. So we really don't have to worry about too many things. All we need to know are these occupation numbers. So that's going to be our next topic, the occupation number representation. So let's do the following. Let's order our single particle states. Let's just write a list of them. Okay, 1, 2, 3, P somewhere in the middle. And if there are infinite many of them, you would go on, right? If there is a finite number, say 500 of them, you would stop at 500. I'm not going to talk now about how you order them. You don't have to worry about that, because what I'm going to say does not depend on how I order my spin orbitals. But you know very well that typically we order them according to the, say, Hartree-Fock energies, or some other form of one-particle energy that you apply, right? People use some sort of an ordering system, but I'm not going to worry about it. It's not important. It's a general theory. Okay? So, what is then a determinant? You know, whether I write it in this way, or say that other way, you remember that I mentioned the anti-symmetrized product of n-particle states. It is isomorphic with a string of zeros and ones. Okay? If I have this ordering of single particle states, then I can say that this is isomorphic with the following ket. I have, say, 0, and at some point I have 1 in a position P1, because that spin orbital is occupied. Of course, it could be leftmost, but let's just be a little bit general, right? Okay, then you have again some zeros maybe. Then you get 1 in location P2. Then you have a bunch of zeros. Then you have 1 in P3, right? And in general, you're going to have maybe some zeros in between. Pn there, and of course the rest will be zeros, because Pn is your last occupied. So I can simply make an equivalence here, or isomorphism, between Slater determinants and strings of numbers, which are simply bunches of zeros and ones using our basis set. So in other words, let me keep writing this. I can write it as simply as follows. Let me write it and then explain. I make an identification between a Slater determinant and a ket labeled by a string of numbers, where here all these n's, little n's, are 0 or 1. In our case, np1 equals np2 equals up to npn equals 1. Those are the occupied single particle states. We're going to use that language, occupied in this determinant. All of the other ones, npi with I different than 1 or 2 up to n, just up a little bit, are 0. Okay? So you can see that now I have a formal language where I don't have to write determinants. I can just talk about these kets labeled by ones or zeros. Okay? So then, what is our space in this language? And what kind of space we're talking about? Please note one thing. If these n's are zeros and ones, and of course that's again Pauli exclusion principle, we know that you cannot occupy the given spin orbital twice, so you're not going to have 2 or 3 or 4. That will be true in bosons, but not in fermions. Okay? But you see here, I can consider a much larger space than we have considered so far, namely a space of these kinds of kets where n's are 0 or 1, and you can have a situation where all of them are 0. That's a state with no particles in it. I'm going to go back to this issue. That's the vacuum. You can have one of these n's being 1 and all of the remaining ones being 0. That's also one particle states. Then you may have situations where 2 of these n's are 1 and all of the other ones are 0. Those are good for 2 fermion problems. Then and so on and so forth. So we are talking about the space which is much larger. It's a space that contains all determinants with variable number of particles in them, okay? Going from 0 to infinity, essentially, right? We call this large space a Fock space. Another important name. Hartree-Fock theory, that's the Fock, okay? In it, for example, okay? We will be, and Fock space is, what did I write?
Quite
Fock
ambiguous
space.
in English whether it starts with an F or a V.
Huh?
It's quite ambiguous in English whether the name starts with an F or a V.
Yeah, so his name is, yes, his first name starts with a V, but this is, anyway, I'm going to write this out. So,
it's a translator, and it's Russian.
yes,
It's
yeah, well,
translated
this Russian pronunciations get tricky sometimes, yeah, because you should see how they write New York. It's N-U, there's a letter U in Russian, and then York is E. It's like written so that you know how to say it. That's kind of actually useful, right? You have to really know. There's always a problem of how you pronounce sometimes some of the English words. The pronunciation and spelling is not the same. Anyway, going back, that's the Fock space. That's a much larger space. So then, what is our space that we talked about before? where the number of particles were fixed, which I will call, actually, by the way, I will call it Hn. Okay, that Hn, if I write it again, okay, will mean a Hilbert space of n fermion states, where n is fixed. Well, it is a subspace in the Fock space. In quantum chemistry, you often say it's a sector in the Fock space, which is simply a bunch of these maybe, let's see if I write NP somewhere in the middle. So we can write N1, N2, dot, 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 NP, dot, 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 okay? Where some, so it's a space, where some of these, all these NPs, from 1 to whatever is the number, say let's make it infinite, is fixed. So you see, right now we have a new concept. We have a Fock space which allows you to form determinants with different numbers of particles. If you want to go back to the language of say determinants here, okay, then the n particle Hilbert space is simply a subspace where some of these occupation numbers is a specific number of particles you have in your system. Okay, all right. So let's just maybe one example. So what if, how am I going to write now a determinant, say, psi1, psi2, psi7, and psi10? Okay, let's again practical notation. What I would also write as phi 1, 2, 7, 10. A determinant where spin orbitals 1, 2, 7, 10 are occupied. Well, right now it's going to become a string where 1 is occupied, so I put 1 there. 2 is occupied, I put 1 there. 3, 4, 5, and 6 are unoccupied, so I put zeros there. 7 is occupied, so I put 1 there. 8 is unoccupied, 9 is unoccupied, 10 is occupied, another 1 here. Okay, and then zeros for the rest. That's what it is now. A binary sort of string versus the original determinant. So now, okay, you know, in quantum mechanics, we always need two things. We need to know what is our space, Hilbert space of functions, Hilbert space in which we're going to operate to define wave functions, and we need operators representing our observables, or operators that we may need for some considerations. Okay, so let's try to talk about this now. As it turns out, and we'll prove all of this, every operator that you can come up with, that you can consider, can be represented in terms of two sets of very simple operators, which we call creation and annihilation operators. Okay? So let me first define the creation and annihilation operators, and then we'll start building more complicated operators from those simple ones. Okay? So let's start with the annihilation operators. You know, if you hear me saying annihilator, I guess that's going to be an annihilation operator. Okay, just so use the shorter phrase. Okay. This is a family of operators associated with single particle states. I'm going to use now a notation that which I used when I was, especially when I was younger, doing my work, and what Joe Paulus uses, what the Piecuch use. So I'm going to use letters X for annihilation operators, labeled with a P. You know, quite often in the literature you see A, you see C, you know, you see letters like this. We don't, you know, I'm not going to use letter A or C to label, to designate the annihilation operators. Why? Because later you will see that little a, little b, little c will be indices we use for unoccupied spin orbitals. So I don't want to write things like A with a symbol A. Kind of looks a little bit weird, right? So we're going to be using X. Okay, so what is then XP? The way you define it is that you have, you know, if you want to define an operator, you have to know how it acts on your basis states. Those are our basis states. These cats in the Fock space. Okay, so you know, the way it works is this. Let me first write the formal definition, we'll try to understand it, and then sort of manipulate it. The way it acts is this. It's going to be -1 to the sum over all occupation numbers preceding level P. So it goes to P minus 1. It's sum over K from 1 to P minus 1 NK. Okay, and then you have NP And then you are changing only an occupation number here from NP formally to 1 minus NP. Okay? That's what it is. Remember that in our case NP equals 0 or 1. So this definition is only valid for such cases. Well, let's try to understand it. If NP is 0, let's continue reading. Well, that becomes 1 minus 0, but that's not so important. We have a 0 here. That 0 here means that XP operator acting on the state in which say a given spinor is unoccupied annihilates it. Produces 0. If NP, and I'll rephrase it in a moment, if NP is 1, let's read again, you get 1 minus 1, that's going to be 0, meaning unoccupied here, and then you have 1. So in other words, the annihilation operators, when it tries to act on a state where you have an occupied state here, then you simply annihilate that particle from that level. So because of this, I'm going to now switch a little bit to the notation used in the handout I gave you, okay, in normal march. Because I'm going to now need for the next some minutes to do some manipulations, and it's going to be simply easier if I don't use this notation, but if I use the notation in march. That notation is very straightforward. What it says is this: when I write right now a cat like this, what I mean is that P is occupied. So that means here NP is 1. Okay? Let's agree on such a convention. If I write P and I cross it out, what I mean is that NP is 0. Okay? And as I said, this is what Norman March and co-authors use in his very famous book, and it's going to be very convenient for what we're going to discuss now. Okay? So if you want to use this sort of notation, then an annihilation operator has the following definition. If you act with it on P being occupied, you end up with some phase factor. I'm going to call this phase factor little m, and we know what it is. It's still written there. It's simply, and the rule is simple, it's a summation over occupation numbers preceding your level P, okay? And then simply P becomes crossed P. You remove that particle from spin orbital P. Okay? That's what it is. If I want to apply XP to a state where P is no longer occupied, then from the definition that I already discussed, if NP is 0 there, you end up with a 0. That's what the annihilation operator is doing. It annihilates when you don't have a particle there anymore. It removes a particle if you happen to have it in spin orbital P. Okay? So, well, you know, it's always good to write one example or two, so let's just write, say, a couple. So what happens if I take annihilation operator associated with spin orbital 3, and I try to apply it to a cat? Let me copy from my notes, something like that. It's consistent with the notes. Okay, so suppose I have a cat like this. I have, you know, which if you really look at it closely, it is a determinant. 3 is occupied, 5 is occupied, 7 is occupied, and 8 is occupied. That would be our Slater determinant notation before, right? What happens when I do this? According to our rules, I'm supposed to remove particle from here. That becomes 0. There are no particles before, so our m factor is 0. You know, so I end up simply with 0, 0, 0. That's where we acted. Then 0, 1, 0, 1, 1, and then a bunch of zeros. Okay? What kind of determinant is this? Well, you can read it backwards now, right? There is no 3 anymore. We just removed it. It has spin orbital 5, spin orbital 7, and spin orbital 8 occupied. You can see we replaced a 4 by 4 determinant by a 3 by 3 determinant by simply removing a row and a column. You remove the row corresponding to spin orbital 3, and you remove one of, you know, the column corresponding to, say, one of the electrons. They're all indistinguishable, so it really doesn't matter how you call them. Okay? So that's how it is. What if I try to remove from here? You can see what's going to happen. The difference, if I try to remove from here, maybe I'll write it as well. Let me put it here. Or actually, since I will be writing more, let's do it here. So if I want to say, continue on this example and say try to remove, try to act with x5, so 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, and so on. And again, according to our definitions, you have to remove a single particle state number 5. Okay, so it's going to be 0, 0, 1, 0, 0 here, 0, 1, 1, 0, 0. But if you count all the occupation numbers before that level, it's 1. So the sign will be minus. Okay, so in this case, if I apply x5 to a determinant which is 3, 5, 7, 8, going back to our determinant notation, you can see what happens is you end up with minus, and then you have 3, 7, 8. That's what it is. Minus because that we removed the next, not the leftmost one. Which, of course, is telling you what you can find in the lecture notes by Joe Paldos, Professor Joseph Paldos. We call Joe Paldos, okay? I can do this. I was his postdoc. You can also rephrase the definitions in a normal language of determinants, if that's what you prefer. Okay, how would we do this? So, for example, if I take, in general, an annihilation operator xp and apply it to a determinant that looks like this, okay? So if p is in the determinant, you just remove it, if it's in the leftmost position. Okay, and this is our previous example, 3, 5, 7, 8 over there, going to 5, 7, 8. Okay, that's going to be P2 up to Pn. Okay, so you can see I removed the P if it's in the leftmost position. If you try to apply xp to a determinant such that this particular P is not among these indices, then you get a 0. Okay, because you already have occupation number 0 there. So it's 0 if P is different than P1, P2, up to Pn. Okay? Alright. Well, you can always ask yourself the question, well, what if my P is not in the leftmost position and I still like to use determinants? Not a problem, because we can use the anti-symmetric properties. So suppose, and I already did this in our example, the 3, 5, 7, 8, you can see what happens. I just have to put the sign. So in general, what you can do is this. Let's just do one example. So what if I have a situation where my P, which I'm trying to remove, is in the middle, between P1 and P3. Okay, so then let's see what happens here. Well, if I want to follow this definition, I don't know what to do actually initially, but what I do is I simply flip these two, then will change the sign, it will produce minus xp P1, P3 to Pn. Okay, so essentially what I did here, I flipped those two. And now P is in the leftmost position, so I can just knock it out. Okay, and I am having minus P1, P3, Pn. You can see it works. So you have now 3 options. You can go back to my original definition with the NPs, you can use the Norman March and Coulter's notation, or you can use the determinants if you prefer. We have 3 ways to write the same thing. Okay, so now I would like to talk about the corresponding creation operators. Before I do this, let me comment a little bit on this one very special state which we describe as the vacuum state. Because it's a little bit, of course, for those of you who know this material, it's already obvious, but for those of you who, say, know the traditional quantum chemistry, that may be new. So here you see we are allowing to produce something which you normally don't do when you use Slater determinants, a state where there are no particles. Because these NPs in our cats can be zeros. All of them can be zeros. So I can have a cat which looks like this. Zeros all the way. It's a sort of, with determinants, that's a funny thing because there's no way for you to write a 0 by 0 matrix, okay, for the determinant. But here we're allowed to consider this. We're going to call this state with 1, 0. Sometimes it gets confusing when it does, then I tell you when it is possibly confusing. Anyway, when I write this, I mean a special state which is simply has zeros everywhere. Okay? we call this a vacuum state. Actually, we'll call this here true vacuum state, because soon enough you'll learn that there is another thing called the Fermi vacuum state. So to make sure that we distinguish between the Fermi and true vacua, which are different, I'm going to say true vacuum state. Okay, for this one. It's a state in our Fock space. So it, like every other state, is normalized to unity. You know, I know it's sometimes funny. When I was young, you know, it was funny for me to look at it. Like, how come a state which is labeled with 0 can be normalized to unity, right? So 0 kind of tells you it should be 0, right? No, 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 it's just a state which is labeled with zeros. It's normal state in this space, and the space that is then spanned, you remember I used the letter Hn, the symbol Hn for the n-particle Hilbert space. So this one spans the space which we will have to call H0. It's a zero particle space, space with no particles. Now, of course, if I taught a quantum field theory class here, that would become a little bit more clear, because, you know, in quantum field theory, that's a natural thing to consider, okay? Where the particles and weight and light, for example, are treated on equal footing. Here, it's a sort of more of an artificial state, okay? And this space is isomorphic with complex numbers. Use this symbol for complex numbers, you know, because simply, you know, multiples of this will, you know, so in other words, if I tell you 5 times 0, well, that's equivalent with 5, right? If I multiply by some complex number, it's going to be equivalent to this sort of isomorphic with the complex number. That's just a technicality, you know. I want to focus on why do I need this state. Of course, it is a natural thing in our definitions, but I need it for consistency. And let me give you one illustration why this state is necessary to consider, although we're never going to compute anything for states with no particles. Okay? But you still have, we need this. So what is a single particle state P in this new notation? It's a state where you have 0, 0, and then you have, you know, I'm using now again Norman March and coworkers notation from their book. Okay? We have, you know, we have P, that P means P is occupied, as I said before. Okay? So what happens if so it's a single particle state. What happens if I apply XP to it? Well, according to our definitions, I'm supposed to knock this out. Right? That's what you know, and there are no states before, so the phase factor is 1. So I'm supposed to end up with a vacuum. You see, you need that vacuum, because otherwise you wouldn't know how to act with your annihilation operators on single particle states. Well, that would be strange, because a single particle state, say, is a hydrogen atom, or a single proton. And we wouldn't know what to do with it. Well, that would be a strange theory, that we can compute a DNA, we cannot compute a hydrogen atom, right? We want to be able to compute all of these in our considerations. Okay, so then of course the question emerges immediately. Well, what happens when I apply any annihilation operator to a true vacuum? Well, obviously from our definitions, there is nothing else to eliminate, so it's going to be 0 for every p. That's for every p, okay? Those are things we need to remember, because we're going to be using them. Simple facts will be sometimes powerful in one or on some situations. Okay, so now I think I am ready to introduce the creation operators. So let's do this. Let's make a little section here. Creation operators. Sometimes I'll say creator. I don't mean the other creator, I mean a creation operator here. It creates particles, as you will see. First of all, how is it defined? Well, it is going to be written as XP dagger. So obviously that suggests it's going to be a Hermitian adjoint, right, of the annihilation operator. And you know, I could stop right here, say, look, you know the definition of an annihilation operator. Creation operator is just a Hermitian adjoint, so I'm done. No, I will not be. So rough on this. Let's go into some details. I will try to tell you how we, because the question is how do I define it? So let's do a little analysis, how I think we should define it first, before I write the formal definition. Okay, so I take XP, and I'll start with this. We already know that this produces a vacuum state. So I'm applying XP to a single particle state. Okay? I get 0. I'm going to take the Hermitian adjoint of this equation, both sides of it. So then you know what happens. Ket becomes bra, xp becomes xp dagger. So that's what I get on the left. And then ket 0 becomes bra 0, the bra vacuum. Okay? And now I will form an inner product of this expression with, that's going to be my notation. You know, when I write a symbol like this, there's some sort of a slash. That means that I'm doing something to both sides of the equation. Okay? That's going to be my way to say it. Okay? I'm going to simply form an inner product with a vacuum of both sides of this equation. Well, let's see what happens when I do that. So, on the left, I get P, xp dagger, 0. On the right, I get an inner product of vacuum of itself, which, as I said, is 1, because vacuum is normalized to unity. Okay? So let's now try to read this. You see, we are having here a situation, we are having a situation here where I have, you can read it in two different ways. You can read it like we started, or you can say, I have an inner product here of P with this, which is xp dagger acting on the vacuum. Remember, our states are orthonormal. So, in order to square it, this must be P. Okay? Anyway, this calculation suggests that that would be the appropriate definition of the annihilation, of the creation operator. So let me then try to write some more about it here. Okay. So we are now suggesting that in order to have a proper definition of the creation operator acting on the vacuum, we should end up with P. Okay? Well, okay, then of course the question is, what happens when I apply xp dagger to some other states in our Fock space? Okay? Well, obviously, this tells you what the creation operator does. It puts particles on various levels. Right now, we put it on the level P. Okay, and I can do this on every other state. So if I go back to our definitions, let me now write a few of them. So, if I want to do it with determinants, so suppose you have a determinant P1, P2 through Pn, and you want to apply the creation operator xp dagger to it. If P is different than all the other P's in our expression, all you need to do is to act in reverse compared to the annihilation operator. Put this P over here. So to produce a larger determinant, the n plus 1 by n plus 1, okay, which will have P in front and then P1, P2 up to Pn, okay? That's when P is left, is sort of, if we assume that P is less than P1, less than P2, and so on. Okay, that is if we use this ordering, that's what happens. Well, what if P is, say, between P1 and P2? Well, let's try that as well. What you do, if you want to continue using determinants, then you're going to simply first put P in front. Okay, so maybe I'll write what I'm doing. I'm doing a situation where P is between P1 and P2. Okay. Well, when this happens, then the first step you're going to take is to add that P in front. So you're going to have P, P1, P2 up to Pn. And then, since P is supposed to be between P1 and P2, you move it there. Okay? You simply permute these two and put it right here. You know what you do this in a determinant, you have to change the sign. So it's going to be minus P1, P, P2, and so on. Up to Pn. Okay? Okay, that's one set of definitions. They're just fine. You can see them in the lecture notes by Professor Joseph Pauli. But let me continue on the definitions. You know, let's do it for using the notation of Professor March and co-workers. Okay? Well, then, you know, what I will have to look at is the following. Suppose I want to apply xp dagger to a situation where, say, P is unoccupied. You know, you remember that's the notation we used. That cross P means there is nothing there. Okay? Well, according to our definitions, you can see that there may be a sign change which corresponds to what you have before a given level. So it's going to be again minus 1 to that m that we used before. And you're going to now put p back. Okay? And this m is simply a sum of all the occupation numbers and k preceding level p. Okay? And if you, now the question of course is the following. Well, what if I'm trying to stick a particle where it's already occupied? Well, you can go back to our determinants. What if I go back here for a second, what if I tried to apply xp dagger where p was right here already? You would end up with a determinant with two p's in it. But that's a 0, because the determinant with two identical rows is 0. Okay? So the annihilation operator, sorry, the creation operator cannot keep creating. It can only create one particle, and then it stops. So if I go back to our normal definition here, that is going to be 0. Okay, that's again, Pauli exclusion principle strikes again. You cannot occupy the same spin orbital twice, and this is guaranteed by our definition. And then, of course, to be sort of more elegant, I guess, in some way, let me write the final formula for it. I guess I'll just this blackboard. You know, remember we started with the formula. We're using the original cats with the NPs in them. So let's, for completeness, have this formula as well, so that nothing is left over. So what happens if I apply xp dagger to a cat where you have NP here, which is either 0 or 1? The formal definition will be minus 1 to our phase factor, which is a sum over nk, where k goes from 1 to p minus 1. I hope you can see it. K from 1 going to p minus 1, nk. And then we have, then we're going to have 1 minus np as our prefactor, and then you're going to replace np by 1 minus np. Let's just convince ourselves that this is right. I'm not sort of making it up or copying from my notes. We're making mistakes. Okay? When np is 0, you read through. 1 minus 0 is 1. 1 minus 0 is 1. You create a particle here. We're fine. If np is 1, well, 1 minus 1 is 0, but what really eliminates the right-hand side is 1 minus 1 here. That's going to give you 0. Okay? So this definition is yet another one. I'm showing you those three, not just to bore you with three different definitions, but you really can find them in various books. Okay? Including books on reserve. So it's good to sort of know them, and you know, it is good to be flexible. So because in some situations you may want one definition, someone else may want to talk to you about, say, the determinants. So it's not good, not bad actually to be flexible in that way. So now, in the final few minutes that I have, let's maybe start talking a little bit about operators. Of course, the next thing we have to prove, the big thing, but that's going to be probably the next lecture, is to prove the properties of these operators, and the most important ones are the anti-commutation rules. I don't think I have time today to do this, so let's just talk about an example of an operator which is kind of useful to have around, which also explains why do we use that phrase, occupation number representation. Why do we say that? Okay? You know, as you can easily imagine, the more complicated operators will be represented by products of x daggers and x's. And if an operator is particle conserving, then you should expect that it will have the same number of x's as x daggers. Because you know, every x eliminates a particle. So if you want to keep the number of particles constant, then you have to have the same number of x daggers. So say a two-body operator in the Hamiltonian will have two x daggers and two x's. So because the Hamiltonian, typical Hamiltonian of a molecule, doesn't change the number of electrons on its own. If you want to change that, you can do this in this language, but that would not be part of the normal Hamiltonian. It would be some other process. Okay? So let's write the simplest particle conserving operator you can possibly come up with. That's going to be the number operator. NP, which is xp dagger xp. Okay? It is very trivial to show. You can do it at home, or ask me if you have difficulty with that. That this is a Hermitian operator. Okay? And let's see then how it works. You can see it's particle conserving because the x is paired with x dagger. Okay? let's sort of see how it acts. So what I'm going to do is a little exercise. I'm going to simply try to apply, erase this as well. Let me try to apply NP to, again, I'm using the notation from normal margin for authors. P is here, okay, occupied, that means P is occupied. I want to now see what happens. So what I do is I'm going to just apply our definitions. Okay, let's assume that we have M here means the M occupied state before level P, as we did before. So according to our definitions, you're going to have -1 to the M, okay, X, P dagger, and you eliminate that P. That's the first thing that will happen. And then in the following step, you apply X, P dagger to this. That means you're going to put particle back in level P. That's going to be another phase factor -1 to the M. So you have -1 to the M times -1 to the M. And you end up with P being back. Well, that cancels out. I mean, produces 1. So you can see that NP acting on a cat where P is occupied doesn't change it. Produces the same state. Well, then the question is, what happens if I apply, move it a little bit here maybe. What happens if I try to apply the number operator to a state where P is unoccupied? Can you tell me? What do you expect if I do this? NP acting on a cat where P is unoccupied? What should I say? 0, obviously, because that first XP will do the job, right? We don't have to do much more work. Okay? But 0 means 0 times the original cat. I want to emphasize that. Okay? Because 0 times anything is 0. Alright? Which means that NP, if I want to now switch to our original notation, if I have NP here, which is 0 or 1, you end up with little np times the same thing. You see, occupation numbers are eigenvalues of these operators. Isn't that great? Okay, you have an operator that tells you how many particles are in your given spin orbital. Okay? So, that's exactly why we call this occupation number representation. If you go back to quantum mechanics classes, you remember when people talk about momentum representation? What does this mean? That means that your basis states are eigenstates of the momentum operator when you build the whole theory. When you say energy representation, what do you mean? The basis states for building it are eigenstates of some Hamiltonian, an energy operator. So when I say occupation number representation, I mean that the basis states are eigenstates of the number operators. That's what they are. So of course, you know, that means that now we can do various things with this information, and in particular, I would say in this class, rarely, but once in a while, and certainly in various books, you're going to see a total number operator. Okay? What is a total number operator? You just sum all these NPs, which are for, every NP is for a specific P, right? So I have to sum them for over all P's. You know, I'm not going to write the range. It's from 1 to infinity, okay? It depends on the basis set, so let's not put anything there. Okay? What is this operator then doing? See, every NP tells you how many particles you've got. So if you apply NP to, if you apply the total number operator, maybe I'll use the next blackboard. That's the final sort of part of this material pretty much today. If I use the total number operator to NP, but of course meaning all other NPs are also present here, that's going to be simply a sum of all occupation numbers in our cat times this cat. Okay? This is simply the number of particles you've got. That operator tells you this. You know, in our course, it's going to be not so important because we always know how many particles, in the end, we'll always know how many particles we've got. You know, there is an area where actually this is an important operator. There's an area called DFT. Density itself doesn't tell you how many particles you have, so you have to talk about the problem of n representability. Okay? There is a sort of old concept of using reduced density matrices instead of wave functions. Okay, by Professor Coleman, revisited recently by Professor Mazziotti from Chicago. in a clever way. Again, what you have there is you have reduced density matrices, not wave functions. So you don't know how many particles you've got. You have to put some constraints, and these kinds of operators bring you that information back. So this is important. For us, it's going to be probably less important, but it's good to have it around. So I guess I will end by saying that next time we'll prove the very fundamental properties of our creation annihilation operators. That is, and let me write them, and that's going to be really the beginning of the next lecture. We'll prove that if you form an anti-commutator of a pair of creation annihilation operator, let me define the anti-commutator. It's like a commutator, but you don't use a minus, you use a plus. Okay? That produces chronicle delta PQ. Chronicle delta, as you know, is 0 or 1. 0 when P is different than Q, 1 when P is Q. Okay? Then the anti-commutator of the pair of two annihilation operators, which is XP, XQ plus XQ, XP, is going to be 0. And the anti-commutator of the pair of creation operators is also 0. Okay? Independent for all pairs of P and Q. Okay, so you can see the only case where we need to get something other than 0 is the pair of a creation operator and the corresponding P equal Q, annihilation operator. Okay, so that's going to be what we're going to start with next time. Today I can't do it, but you can already start looking at your homework. You are supposed to prove there, actually, this and this property. And the way we're going to do it is that I will prove to you how to handle this case, because it's a little bit more elaborate. And you will apply the same recipe to the other two. Okay? So it's not going to be a difficult homework, but it's going to be a good practice for you to do what I do here. Okay? So thank you very much, and I'll see you on Monday at 8:30. Thank you.